Okay, so what are we going to be doing today? More exercises. So far, this has helped me a lot with exploring. Uh, so far, the only thing I can do is really Firefox QM exercises. So the only thing that I've been able to do so far, or the thing that I've managed to learn out of these is from these first exercises, I did explore the concept of, sort of R, like 3D space, and then sort of doing this kind of circular integrals or polar integrals. Then we learned about uh, the thing with momentum, right? So that was actually this is something that I will definitely be digging into a bit more at some point. But out of these, what I kind of understood is, well, the wave function is not what I thought it was, right? So this was kind of the aha moment. I was like, I always thought and I always understood the wave function as it's the equivalent of whatever variable, um, whatever dimension you're looking at, like classically, right? So classically looking at things like position, right? So the wave function of position would be then position. Um, but it turns out the wave function of position encodes also momentum. Um, so it's really more. It's not just you can make that like analogy of like position equals. It's not the same kind of level of citizenship, so to say. Okay, so show probability density of finding the particle with momentum. Uh, and I zoom these in. Page width. Show that the probability density of finding the particle with momentum h bar k is isotropic. So it does not depend on momentum. I'll work on the details later. I'm just trying to find what is going to be what is going to maximize my learning. So again, doing just the 80%. Show that the spatial probability density is this just I don't understand. Okay, it's also isotropic, so it's just calculating that and then show that it's isotropic. Um, this leads me to the question of like, is there? But that's more of a technicality, right? So how do I ChatGPT? Um, login, come on, login. How can I check that a wave function is isotropic? Is there like a how can I check the function? I don't know if there's like a. I guess it's just a set of like a recipe for these, right? So. Direction of your approach. I guess it's a combination of just doing an analysis. It's just doing an analysis, so that's all fine. Okay, but calculate the expectation values. So this is let's dive into expectation values. Okay, of position and momentum at time t. I'm going to show that the expectation value of r squared. So the question is, what does this mean, right? Increases with time, and it satisfies this inequality. First of all, let's just dive into expectation value. So new chat. So let's ask GPT, what is the expectation value of? It's really, it's an expectation. The expectation value is the observable, right? That's the right way to ask the question. So essentially, you have the position operator, the momentum operator, and sort of what are the expectation values. Let's just do the classic Google. So what is of the position? Let's ask it to be more concrete of the position operator. Hyperphysics. God. We're you know, it's kind of like, I like approaching it like this because it helps me kind of pin all these different key elements, right? In quantum mechanics, expectation value of an observable is the average value that observable when the system is in a particular quantum is the average value of that observable when the system is in a particular quantum state. The expectation value is calculated by taking the inner product of the observable's corresponding operator with the state vector of the system and then taking the real part of the resulting complex number. For example, I'm not so sure that's correct. Okay, so that's important. Let's cross check that with the Google search, but expectation value of A in the state psi is given by these. Now, I guess I'm also looking for an interpretation of these, or what is the okay, in the continuous setup, it seems like we're doing an integral of, to relate quantum mechanical calculations to something you can observe in the laboratory. The expectation value of the measurable parameter is calculated. For the position x, the expectation value is defined as whatever x is, right? So is this the position operator? This integral can be interpreted as the average value of x that we would expect to obtain from a large number of measurements. Okay, so the expectation value is just an average of what you expect from a measurement perspective. A lot of these concepts, what's interesting is that I'm not so sure how well they map to a super deterministic view on quantum mechanics. Because when you get into measurement, that's what, and measurements being correlated with the detector settings. Alternatively, it could be viewed as the average value of position for a large number of particles, which are described by the same wave function. For example, the expectation value of the radius of the electron in the ground state of the hydrogen atom is the average value you expect to obtain from making the measurement of a large number. Okay. Well, the expectation value of a function represents the appearance of an average of the function. The expectation value of momentum involves the representation of momentum as a quantum mechanical operator. While the expectation value of a function of position has the appearance of an average, the expectation value of momentum involves the representation of momentum as a quantum mechanical operator. That's an equal position. Where this is the operator for the x component of momentum. Since the energy of a free particle is given by this, then the expectation value for energy okay. It's like that, okay. For a particle in one dimension. So you do multiply by the, it's like you do the operator. Now, why does this make sense? Why mathematically speaking, is disintuitive. What's the, again, in a way, it's like, what's the meaning of is that the transpose conjugate, or what is that? The why does this make sense, right? So multiplying the operator with the wave function makes sense because you're basically saying you want to get, for every x you basically apply and want to get the or you just apply the operator, right? And you want to get the, so you're basically what is the result? I mean, what is the result really? The thing is, mathematically speaking, like, what is the result of applying an operator, right? What is the result of applying an operator to a wave function? Because it's still a function, right? Operators, like, there'll be more operators. Triangle's equation. We begin with a reminder that the state vectors are written in terms of the basis vectors of each space as follows: position space, although in most cases, acting as same state vectors. No. But I mean, if that's the position operator, like, what the heck does these? What is it? What is it that it actually gives you? Right? You have a wave function. You apply this thing, and that's kind of like another function. You know what I mean? It's like, what I'm trying to see is what is the. So we're trying to break down basically intuitively what that means, right? So if you take like an average classically, which is what's an average, right? Like, what's really the definition of an average? The expectation value is exactly the same, but like, what's the average is like? I mean, what's how do you interpret an average, right? That's maybe the mean and the median. Is the mean the same as the average? I think so. Yeah. Iron blue. So you have the mean 100. indicate where the center and of the data is located and what the typical daily number of newspapers hold is. Yeah, that's kind of like, yeah, okay. It's in a way, it indicates centricity. It indicates like it's just very. I mean, how you interpret it depends on the context, I guess. But it's like the center of things, right? So it's a kind of a center. So essentially, what the expectation value will tell you is the same, right? So if you, but that's what I'm thinking is like if you have a wave function, and then when you apply the position operator, the idea is that applying the operator is like measuring, right? Is applying an operator to a wave function, same as measuring. I mean, that is what I assumed up to this point, right? So, this is a good thing. It's a function over a space of physical states onto another space of physical states. So, on the formulation, quantum mechanics operators in quantum mechanics of operators. The wave function. Okay, so if psi is an eigenfunction of the operator A, then it will really give you, so that is the eigenvalue of the operator, measure value, corresponding to the measured value of the observable. If psi is an eigenfunction of a given operator and then a definite quantity will be observed if a measurement of the observable A is made of the state psi. Conversely, if psi is not an eigenfunction of the operator, then it has no eigenvalue for A, and the observer does not have a single definite value in that case. Instead, measurements of the observable A will yield each eigenvalue with a certain probability. So essentially, but what is it that you're expecting to, so what you're expecting to have after the operator is applied? That's actually an interesting topic because this is like, I like breaking this down, you know, kind of getting at the bottom of the definition is kind of, that's what's complex, right? So where space vector, each component will yield the corresponding eigenvalue acting these on the wave function. So if you multiply the eigenvector, the operator by the wave function, then it's like you get a sum. And here's now the expectation value. Okay? So position. Yeah, it's funny, right? Because position operator is just these. That's the general definition. So it's basically Why? So why is that the case? If I have a wave, so can you give me an example of wave function in the 3D space, position space. Okay, yeah, let's take that. So you have meaning that it is equal to 0 at the walls of the box and non-zero elsewhere. Oh my god, stop with this answer. Okay, so that's an example of a wave function. That's okay. Can you express the wave function above and polar coordinates using only the variable r? Can you do that? Certainly. Okay. That's all fine. And then the question would be now, applying the position operator. I'm confused. I don't know if I'm explaining myself well, right? So what I'm trying to understand here is, what does it even mean to apply the if that's the operator, okay? Kinetic energy, total energy, Hamiltonian angular momentum, spin angular momentum, total angular momentum. How? Let's one dimensional. Let's start with an easier case. Can you give me a simple one-dimensional wave function and position space? In a one-dimensional box. Let's plot these. Come on. Is Ghostwriter gonna eat that up? So if I say main, why am I using main here? So if I say main and I say generate code and I ask it like, can you plot these? Just non-clear backend. How do I solve this? I think I did that before already. copy. How can I solve this warning? So we go to main. If I run this, it should work now. Oh yeah, wave function for ground state of a particle in the box. One-dimensional. So the thing is, what does it mean to just multiply that by x? And now we want to plot psi times x. How do I get Ghostwriter engaged again? That's what I've done. Do I just generate code algae? Okay. Plot psi times x now. What? Whatever, just x. Nah. Yeah, but I should remember. I guess I just do. I guess just plot x psi, and then psi. What if I just do psi times x? How different it is, right? So now we have this shape, and what? And now that's the shape. What does this even tell me? Can I plot psi and like, so how can I overlay two plots and matplotlib? So I guess subplot. X1, plot the first data on the first subplot, plot the second data on the second subplot. So stop. Okay, so if I just copy these, I just say, well, essentially, so plots 1, 2. So this is yeah. So this is one plot, and then this is times x. Will that work? And all of it here. So I think that should be, that's where we're going. So I'm trying to understand try to understand very slowly, right? So I'm trying to understand what is the meaning of taking a very simple wave function, multiplying it by the position operator, just being these. Why? What is these? And what is this giving me at all? Okay, so it does not overlay them, but okay, it compares them like that. I assume I'm doing that correctly. So yeah. Okay, so. Mm. Mm. Is that the wave function though? Is that correct? Like the wave function that it gave me here at the beginning? Square root of, yeah, and then pi times x divided by yeah, exactly. And so, okay. So why? I mean, this is supposed to give me what? What is it supposed to give me? I don't know. Is this supposed to give me? It's another function, right? But it doesn't really. I don't know what it is that it's telling me. Like, what have I transformed it into right now by applying the operator? Um, yeah, I guess that's going to be for next video. Cool.